right, so chair conformation. Gonna make this one quick, easy, not too much detail. So 3 things we're gonna go with: how to draw the 2D representation of the chair, the ring flipping process, and the higher and lower energy chair conformations. So let's start with drawing the chair. And before we do that, let's look at a chair. All right, so right here, we've got ourselves a chair, okay? Or 6-ring cyclohexane. When we look at it flat, it looks kind of like this. And you know what, let me take out these substituents for now. When we look at it flat, it looks like this, okay? Nice little cyclohexane. But if we turn it, we get a chair conformation. Flat, chair conformation, okay? And when we do our substituents, we can have axial. Just our axial, they look like this, they go up and down. Or we can have equatorial. They look like this. They go to the side, okay? Now something important is, let's say we are drawing our molecule and it says that this red one right here is in the front. So our flat 2D is in the front. And this one right here is in the back. It is in the back. In the back, this one's in the front. Okay? Flip it like this. We see that this is what the chair conformation would look like. This one is axial pointing down. This one's axial pointing up. Front, back, axial pointing up, axial pointing down. So general rule is that when drawing these, axial forwards, like the ones that are facing in front towards you, tend to be every other one. So that means this one right here, and this one right here, they will all be facing towards you, and they're the axial ones. Ones facing behind will be this one, and this one, okay, for axial. How about equatorial? Well, it's just the ones that are kind of, I guess, in the middle, you know? It'll be easier for drawing, I'll show you guys later. But this one here, this one's pointing in the back, away from you. This one's pointing towards you. Equatorial, look like this. Towards you, away, towards, away, towards, away for equatorial. Axial, same idea, towards, away, and so on and so forth. Show you guys with a drawing. All right, so here we've got our cyclohexane drawn right here and the chair conformation, right? Flipped it. Okay, I can't say we flipped it, but you know. Draw this chair conformation, really simple. Just go zig, zag, connect, connect, long, long, okay? And it should be going downwards. And that's it. That's how you draw it. It's really not the hardest thing ever. All right, so wedges and those facing behind. How do we do that? Start here. I'm gonna quickly draw this diagram for you guys. The ones in red right here are our axial, okay? So I'm gonna draw out the axial ones. As you see, it kind of follows this pattern I was talking about earlier. That's towards you, behind, towards, behind, towards, behind. Towards you, behind, behind, towards, behind, behind. Like that. And then the equatorials, which I'm going to draw in blue, follow a similar pattern, but they're the opposite of the axials. By that, I mean wherever the axials are behind, the equatorials will be facing towards you. if the equatorials are facing towards you, sorry, if the axials are facing towards you, the equatorials are facing behind. Towards, behind, towards. Towards, behind. Should be axial, but all right. So if I want to draw this as a ring and label each of them, like where would I put my substituents? 1 corresponds to 1. Well, the substituent here will be over here. Okay. Substituent here will be right here. And so on and so forth. 2. This one here corresponds to this one here. This one here corresponds to this one here. This one here corresponds to this one here. This one here, 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 whoa, here, 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 finally here, here, and this should be all right. So go ahead, take a screenshot. All right. It's important to note though that when you draw these, always make sure that if you have large substituents, that they're always drawn equatorial. So they're drawn on the blue ones here, okay? And more on that a bit later. Okay. Now, how do I draw a Newman projection of these two? So I'm gonna just make them a bit smaller. Well, there's actually this really neat trick to drawing one. I'm just gonna go ahead and draw our basic Newman projection setup, and I'm gonna face mine downwards this time. I'm facing them downwards because I'm looking this way into the molecule, and this is up and the back is down. I'll show you an easier way to visualize that in a moment. I'm gonna draw them like this because that is the low energy conformation, the best one you can have, right? Remember the, I think, Sin-Perry-Planner, something or other, the staggered conformation. All right, what now? What's going on? So for our conformations, what you want to do, and I'm going to switch my substituents, put one here, is you have this, right? You want to kind of grab this one and then grab this one on this side. And this is kind of how you visualize your Newman conformation. Let me add like another substituent here to make that a bit easier. Maybe just don't mind too much the colors and all that's pretty irrelevant. I'm not like making a specific molecule. Okay. This should make it a bit easier for you guys to visualize. Grab onto the sides. This is the front of your Newman molecule. Then if my hands are transparent, you see that you can see the back kind of forms that. This is like the circle of the Newman thing, right? And it forms that thing in the back right here. So let's draw it. All right, so let's go ahead and draw this. What we can see here is that we've got our axials, one going down here, one going down here, one back here, and another back here. And then we've always got like one here and one here, okay? And then we've also got our equatorials. 1, 2, that's not the equatorial. One of them is sticking out here, one of them going from behind over there. 1, 2. All right. Now let's label them with their numbers. So this one here corresponds to this one, which corresponds to this one. Okay. 1 is going out, essentially out of the page. Or I guess, to show that this is the axial. Okay. And then what we have is we have our second one here. This one here. It's supposed to be going into the page, but not really all that well drawn. Got 3, right? Number 3, 4 corresponds to this one and this one. This one and this one. On this side, or still on this side, we've got 5, 6, 5, 6, 5, and 6. Got on this side, or in this right here, we'll start here. We've got 7, 8, 7, 8. Got 9, 10, 9, 10, 9, 10. Finally, I've got these two, which is 11 and 12. And that is how you draw your 2D molecules. All right. So go ahead, take a photo. Now we'll start with ring flipping. Oh, and before I erase this, it is important to note that if you got like big molecules, always draw them on the equatorial. More on why a bit later. Okay. Okay, so for our ring flipping, basically what happens, I'm certain you've been told this, is that axials become equatorial and equatorials become axials. And no, it's not this. Oh, wait, let's just break them in. Oh, the ring was slipped. No. More annoying than that. What really happens is that, let's put these back on their original. So these go up, these go down, and the ring is flipped. Okay, show you that one more time. These go down, these go up, the ring is flipped. Up, down. The ring is flipped. Up, down. The ring is flipped. One more time. Up, the whole one up, down. The ring is flipped. This one up, this one down, down. The ring is not entirely flipped because I fucked up. Yeah, okay, yeah, whatever, it's flipped. Okay. All right. All right, so how do we draw these ring flips? Well, what we do first is obviously draw our ring itself. And let me just do a quick undo here. Just clear these two. We're just going to use this one here because it's already numbered 2. Basically, what happens is that first, we got to realize that this was a pretty bad idea. Yeah, it'd be easier if we just start over. Let's go ahead and draw a ring. Up, up, connect, connect, down, up. All right, here's our ring. We have substituent A and B, and then we're going to flip it. So when we flip our ring, what happens is we take this right here, right? We take this right here, and we quite literally flip it. Oh, I flipped it wrong. There we go. We flip it. Do you see now how they are flipped? They are kind of symmetrical to each other. Just bring this one down. They're kind of symmetrical to each other. Yeah, they're flipped. And what happens is that these substituents, they all move up a carbon. So they are now going to be right here. Hope you guys visualize that. Essentially, if we go ahead and we started here and we flipped it, we've moved up to over here, okay? And so it will be right here in the mirror image, if you imagine it as a mirror image. And this one kind of corresponds to this one here. This one corresponds to this one. This one to this one, and so on and so forth. So if we were to flip and the substituents were over here, they're starting here, then they would move up one, they would end up here. They would end up here when we flip it. All right, and just a quick reminder, A was axial, now it became equatorial. So remember to just redraw it like that. B, same thing. Equatorial became axial. All right. And that's how you flip your rings, pretty much. I guess an easier way to label these. You can go ahead and label them. Let's say we've got these carbons, right, on each of them. Take a red. So we've got 1, 2, 3, 4, 5, 6. So when we flip, we're going to get 1, 2, 3, 4, 5, 6. This is kind of more we meant when they move up a carbon. And just remember to draw your axials as equatorials and your equatorials as axials. However, axials that are pointing down will remain pointing down. So what is pointing down will remain pointing down. What is pointing up will remain pointing up. So go ahead and take a photo of this. Show you guys what I mean by that. This axial here is pointing up, pointing towards me. This is one of the ones that are pointing towards me. So when it's flipped, it is going to point up. It is not going to point away from me. It is going to point up. Equatorial, same idea. It is pointing down, away from me. It will point down, away from me when it is flipped. It is pointing up. Wait, let me check that. Down, up. Okay. It's pointing up towards me. Okay. And this one is 1, 2. It'll be over here. It's pointing up towards me. All right. Remember, I'm looking at the molecule down this way. That's how I usually look at it. Maybe might differ sometimes. All right. So now we're going to go into chair conformation energy. All right, and this might seem a bit confusing at first, but let's just take it kind of slow. All right. So there are kind of like 3 ways that you can have some repulsion in the chair conformation. You can have this 1,3. What's it called again? 1,3 diaxial repulsion. Diaxial we can have flagpole interactions, or you can just have, what is it again? Some ring strain. No? Unfavorable gauge interactions. Gauge. Okay, so let's take them one at a time. So 1,3 diaxial is when you've got a big substituent that's not a hydrogen here. You've got some hydrogens here. And what happens is that they're all kind of facing each other. Kind of form this like ring between them. Here's our big substituent. Here's our hydrogen. Here's our other hydrogen. And this is your 1,3 diaxial repulsion. What happens is that this guy right here, they're kind of taking up on each other's space. It feels very annoying. It feels very crowded. It increases steric repulsion between them. It is annoying. It is crowded. It is steric repulsion. All right. Flagpole interactions. And I think this might be easier if I do it with Newman or, no. Okay. Flagpole interactions happen when the chair conformation has this thing called a boat conformation. What's a boat conformation? Well, remember when the chair was flipping back and forth? Boat conformation happens during that flip. Okay, the molecule doesn't actually stay in that position. It's just kind of like an in-betweener, okay? Like something that happens between while the molecule is flipping. But you should still know about this. So I'm going to draw a boat here. 1, 2. 1, 2, 3. Okay. And what happens is that you're going to have these two hydrogens here. They're going to face each other. And similar to the 1,3 diaxial, where the substituents are kind of in each other's space, these dudes are also going to be up in each other's space. And it's really annoying. So creates repulsion between them, and it's going to create some strain in the ring, some uncomfortableness within the ring. And finally, you've got your gauche interactions. All right. So your gauche interactions is what happens when you, let's draw Newman. No, it doesn't happen when you draw Newman. Okay. A lovely little Newman structure drawn there. And let's say we've got our extra substituent right here. And what's going to happen is there's going to be like a gauche kind of positioning between the substituent and this carbon and this carbon. Okay. And what happens is that there's going to be some repulsion as a result. It's like this substituent is way too close to this bond here, and it's also kind of close to this one. So it's going to end up creating some strain. We can fix this, however, if we go ahead and draw the substituent in an axial manner. So this time, the substituent is up here. And instead, what happens is that we get favorable, these kind of anti-periplanar conformations instead of the gauche right here. Get kind of like that, you know, instead of a 1, 2. And this is actually why we like to draw our substituents as being axial instead of equatorial. When we draw, this is why we draw them as equatorial instead of axial. When we draw them as axial, we get that 1,3 diaxial repulsion. Remember when they were in the chair conformation? There's that kind of triangle of hell that was connecting all of them. They were all up in each other's faces. 1,3 diaxial. And then we have our gauche, unfavorable gauche interactions, which is when these guys here have a gauche conformation with this guy here. And same idea, encroaching in each other's space, creating ring strain. So we fix that by making the substituent equatorial. We now have an anti-periplanar relationship, and we don't have 1,3 diaxial repulsion. And this decreases the amount of strain in the molecule. When we decrease the amount of strain in the molecule, we decrease angle strain, so that's just the angle between the carbons, and torsional strain, that's just strain within the bonds here. Okay, so angle strain between the carbons, torsional strain in the bond. All right, and this is great because that means, well, we have a low energy conformation when the substituents are equatorial. All right, another key point though is that the axial arrangement of a large substituent, like a really big fat guy right over here, it's destabilized, right? It's uncomfortable, which means that the molecule will have to shift itself, will have to flip itself so that it will make sure that that axial becomes equatorial. In other words, if the substituent is small, it can be axial, it can be equatorial, it's completely fine. But if the substituent is some big fat one, like an absolute unit, well, it's going to rotate and flip itself to make sure that that substituent is equatorial. In short, you can say that, yeah, the substituent does control which chair conformation you have. So I guess in the end, the substituent is in control. And depending on its size, the cyclohexane or the chair will take different conformations. Oh, and just remember that the two chair conformations we saw earlier, the ones that flipped into each other, those are the lowest conformations, okay? And I told you it's their boat conformations that they go through in the middle. So here, let me go ahead and illustrate that. We've got our two classic chair conformations. Zoom in. One, copy, paste, two, okay? These are the lowest energy conformations. When they ask you to draw the lowest energy or the chair conformations, or even the conformers, like every conformer, these are the two that you're going for, the original chair and the flipped. In between, there's a bunch of really weird shit. Like, it's really weird. You've got this half chair conformation, another half chair here, and you've got the boat. I'm not even gonna draw them. I don't think I can, at least. Boat, twist boat. And basically what this is kind of a roadmap of what the chair has to go through to get to this one. Goes from its classic chair, becomes a half chair, it becomes a twist boat, full boat, tries to untwist itself and ends up becoming a twist boat again, becomes a half chair. Finally, it reaches to the flipped chair conformation. So these guys right here, these guys in the middle, guess what? You can know that they exist, but you probably won't be asked to draw them. Or at least I hope not. I really hope not. However, these two, when they ask you for the chair conformations, these are the two guys you want to go with. All right, quick video. As always, if you have questions, go on my website. Should be linked in the YouTube About section. Feel free to ask questions. There's a Google form there. Hit like, subscribe, turn on those notifications. Yeah, hopefully this video was helpful. All right, awkward goodbyes. And where is the stop recording?